All right, so this lecture is going to be on the hydroboration followed by oxidation reactions for alkenes. These are also addition reactions. And just like the previous slide, what's being added to one carbon, one of our vinyl carbons is going to be a hydrogen, and the other one is going to be an OH group. The difference is that these are going to be anti-Markovnikov additions of these two. Okay, so that's the big shtick about these reactions that are different than the previous lecture. Both of them are ways to form alcohols. This one will form an alcohol group on the less highly substituted carbon, the anti-Markovnikov regioselectivity. All right, hydroboration and oxidation, why is it that name? Well, because relies on this borane here. This is the key player, BH3. Okay, THF is the solvent that it's in. The key here is going to be this boron compound, the borane. So what happens is you first react it with your borane, and then you follow it up with actually another peroxide and a base here in order to get the OH group. Okay, but that's where the name comes from. Hydroboration rather, comes from the fact that the key player in these reactions is going to be the borane. Okay, so if I have this reaction here, again, I'm going to have addition on one of these two vinyl carbons, and this is going to be on the less highly substituted carbon, right? In addition, these are Syn additions, right? So different from last time, we had anti-additions, where that meant that the hydrogen and the OH group were attached from opposite sides. Here, they're going to be a Syn addition, so both of them are going to be added to the same side. So in this case here, first, notice I have substitution of that alcohol group on my less highly substituted carbon, right? An anti-Markovnikov. But then also importantly, my OH group and my hydrogen have been added to the same side. Okay, so I will get a mixture of these two enantiomers, where again, the key thing is that the hydrogen and the OH group were added to the same side. And again, OH group always on that less highly substituted carbon. You're not going to see the anti-products. So let's just take a look at those real quick, right? So all four of these together would be all the four possible stereoisomers of this compound, right? But I'm only ever going to see two of them. And that's the two that result from the Syn addition. The anti-addition, notice how that would mean that the hydrogen that was added was on a different side than the OH group. That's not going to happen. Same over here. This is just the mirror image of that. That's also not going to happen, right? So the anti-addition is not observed. You only have the Syn addition. So let's take a look at why this occurs. It actually, one of the reasons is that the borane looks a lot like the carbocation in terms of its geometry. What makes a borane molecule a good electrophile is just like a carbocation, it has an empty p orbital, okay? So what happens in this reaction, the first step is we have our double bond doing what pi bonds do, which is to play the role of nucleophiles or bases. Those electrons are going to go and attack that empty p orbital in the borane. But then what's going to happen is you're again going to form this sort of complex where the borane is going to be associated with that less highly substituted carbon. That's because the positive charge wants to form on the more highly substituted carbon. Right, so essentially what you have here is a complex where you have the p orbital of your boron interacting with one end, and then you have the p orbital of this carbocation interacting with the hydrogen. Okay, so it forms this complex, which results in the hydrogen going on the more highly substituted carbon. Okay, then the next step is to follow it up. That last step is that oxidation, which replaces the boron within the OH group. Okay, but importantly, you see that this will lead to the anti-Markovnikov product. And then it's a Syn addition. So let's see what that means real quick. Well, if we have one chiral center, we'll end up just forming both pairs of enantiomers, right? So again, let's just note that this would correspond to my less highly substituted carbon, right? And this is, you got to remember about with these syn and anti additions. They all sort of arise from the fact that alkenes, those double bonds in alkenes, are flat, right? All 1, 2, 3, 4, 5, 6 of those atoms are lying in the same plane. So this means that the hydrogen and the OH that are going to be attached they can go from either side, but more importantly, they have to come from the same side, right? So they're either both coming from the top in a Syn addition, or both coming from the underside in a Syn addition. So when you only have one chiral center that's formed, you'll see that you get both stereoisomers out of there. The difficulty comes from what happens when you have two chiral centers, and this is where the Syn addition is actually pretty consequential. You have either your OH group and your hydrogen both coming from the bottom, or both coming from, right, like into the plane of the page, or they're both coming from the top, so they're both wedges. If we wanted to sort of see, so notice that you get a pair of enantiomers. Again, just like before, there are actually 4 possible stereoisomers of this compound, but you're only going to get 2 of the 4. One way to do this is to think about a Newman projection, right? So let's say that I'm going to look down this carbon here. A Newman projection for an alkene, you always sort of have that eclipse structure. As I've drawn it over here will be my CH3, and on my back carbon, that's now this ethyl group. On my front carbon, there's an ethyl group, and then on the back carbon is a hydrogen, right? So now I'm gonna have, and I guess importantly note that the back carbon is going to be the one that's the less highly substituted one, so it's gonna be the one that gets that OH group. Well, importantly, when I form my new Newman projection here, I need to make sure that both the hydrogen and the OH group are being added to the same side, right? And again, you're gonna have an eclipsed structure here. Okay, which you can rotate and see that that corresponds to one of your enantiomers. If you had it going the opposite, where it came from this way here, you would see that you would form your other pair of enantiomers. Okay, so this is by using these Newman projections, you can make sure that you arrive at the correct stereoisomers. Sometimes it's a little hard to see just from the bond line drawing. Once you get good at it, you'll be able to just do it here. You know, noting that these dashes appear on the same side, right? And that means that these guys, this one's pointing one way and this group is pointing the other. Okay. But yeah, these are the sort of getting the stereochemistry right is going to be one of the challenges of this particular lecture, and it's just going to be practice, practice, practice. Using your model kits will be very helpful as well. Okay, so let's take a look at another example here. I have 2 vinyl carbons. Which one is going to actually receive that OH group? Right? So anti-Markovnikov addition, so it's going to be the less highly substituted. And then importantly, I'm going to make sure to add my hydrogen and my OH group to the same side, because this is a Syn addition. Notice neither of these is going to change the stereochemistry of this top methyl group. But I'm going to either have both my hydrogen and my OH group added to one side. That means that this Pointed down is the methyl group. Alternatively, they can both be added to the other side, which means that now pointed up is this methyl group. Okay, so again, just practicing those Syn additions. Notice in this case that what's produced is not or not enantiomers rather, because we had this third stereocenter here that kind of messed that up. So just beware, it's not always a pair of enantiomers that's produced, particularly if you have another stereocenter there. Okay, so now let's just create a little cheat sheet for these particular reactions here, these hydroboronation reactions. So first of all, the reaction mechanism. Do I expect you to know the reaction mechanism? No, you don't have to draw the reaction mechanism from scratch for these. What you do need to know specifically about the regioselectivity is that this will produce the anti-Markovnikov product. And then lastly, in terms of stereoselectivity, these are Syn additions, which will influence the reaction products that you get. All right, so again, above here, I could actually draw 4 different stereoisomers, but I'm only going to get this pair here, this pair of enantiomers, because of that Syn addition. My hydrogen and my oxygen are added to the same side.